Okay. So, calorimetry. Final lecture for today. So, constant pressure calorimeter, aka a coffee cup calorimeter. Q equals mc delta T equals delta H. By measuring the change in temperature, we can measure the heat change, which means we're measuring enthalpy, which is almost, but not quite, internal energy. But be aware, we are not measuring Q directly. That's important. It matters for the sign. It matters for making sure you're getting everything all lined up. You have to be aware of system and surroundings. So, if you are dissolving salt in water, okay, the system is the salt. Okay, the surroundings is the water. Meaning that when you dissolve salt in water, it will undergo that change. It'll undergo the reaction, as it were, going from solid to aqueous. Hey, Jason. Therefore, when it undergoes that change, it will undergo a change in energy. It'll undergo a change in temperature. Okay? But the temperature change you're measuring is the temperature change of the water, meaning you're measuring the temperature change of the surroundings, not the temperature change of the system. So the calorimeter measures the surroundings in order to measure the system. Okay. All the heat lost by the system is the heat lost to the surroundings. Any heat gained by the system is gained from the surroundings. So the heat change of the system is equal and opposite the heat change of the surroundings. So for the reaction taking place in solution, the heat change of that reaction is negative the heat change of the solution. Therefore, the heat change of the reaction is negative mc delta T for the solution. So, for example, you mix 50 milliliters of 1 molar sodium hydroxide with 50 milliliters of 1 molar hydrochloric acid. The solution temperature increases from 22 degrees Celsius to 29.5 degrees Celsius. Okay. What is the heat released by the reaction? And what is the enthalpy of the reaction? Crap. Okay. My laptop is screwed up again, so I'm going to have to try and do this on my regular computer. Okay. All right, so we have Q of our reaction is negative Q of our solution. It's negative mass of our solution. The mass of the solution, let's MC delta T. Okay. So the mass of our solution is going to be this mass here plus this mass here, because we're mixing the two solutions together. Okay. So 49.9878 plus 50.0110. Okay. 99.9988. Okay. So negative 99.9988 grams. The specific heat capacity I gave you, again in the problem, was 3.878 joules per gram degree Celsius. It's not quite the specific heat capacity of water because it's not pure water. So 3.878 joules per gram degrees Celsius. And then our temperature change, I also gave that in the problem, 29.495 minus 22.120 degrees Celsius. So that's the mass of the solution, the specific heat capacity of the solution, and the change in temperature of the solution. And once again, we can plug those numbers into the calculator. So 99.9988 times 3.878 times 29.495 minus 22.120. For a total of 2860. Okay, let's see. That would be 4 sig. Yeah, so we're limited to 4 sig figs here. Okay. Equals negative 2860 joules. So that is the heat change of this particular instance of the reaction. But I also asked, what is the enthalpy of reaction? Okay. So the heat released by the reaction is what is the amount of heat released by this particular instance of the reaction. Enthalpy of reaction is sort of the general change for the total reaction. Meaning, it's the difference between how much gas you use for this particular car trip versus the mileage your car gets. Okay, how much energy for this particular mixture, how much energy for the reaction generally. Okay, miles, the gallons you use for this trip, the mileage overall. Okay. So the way you look at that, the way you do that is delta H equals Q over N. All right, so Q is just the energy for that reaction. N means, moles for this particular reaction. So that would mean finding the limiting reactant so that you know how many moles have been used up, or how many moles to normalize it by. In this case, it's the way I set up the reaction, it's exactly the same. We have 50 milliliters of 1 molar solution for NaOH and HCl, and NaOH and HCl is a 1-to-1 reaction. The limiting reactant is the same number of moles either way. So 0.050. Oh, yeah, 50 mils of 1 molar. Okay. So the number of moles is 0.05000 moles. Again, that comes straight out of the problem. 50 milliliters is 0.05 liters times 1 molar, or 1 mole per liter, means 0.05 moles. Okay. So now 2860 divided by 0.05 molar. We once again break out the calculator. So we divide by 0.05, and the result is 57.120 kilojoules. Okay. So negative, 57.20 kilojoules per mole. So remember, the enthalpy change of a reaction, you take the specific instance of the reaction and you divide by the limiting reagent, okay, just the number of moles of the limiting reactant, in order to get from Q to delta H. And don't forget your negative signs. Be sure you got the sign convention correct. When you mix hydrochloric acid and sodium hydroxide, it's going to produce a lot of heat. The solution will get quite hot. It's not like what you see in the cartoons. It won't be an explosion. Instead, the solution could boil, and thus you'd have acid and base frothing all over the place and boiling water. That could be bad. It would be a bad thing if you mixed these in cautiously, but it wouldn't explode. So Jason, feel free to type in your question anytime. I'm still monitoring the chat, so I'll see it when you ask it. All right. So a bomb calorimeter is different from a coffee cup calorimeter. Very similar, but different because it's at constant volume, so it has a different formula. So Q sub V, remember Q at constant volume is equal to the change in internal energy. So the Q of the reaction is still negative Q of the calorimeter, basically negative Q of the water. But that looks different because it's going to be negative C delta T. Bomb calorimeters are very well calibrated. They're very, very well constructed. They always hold a specific amount of water, and they always have a heat capacity instead of a specific heat capacity. Specific heat capacity means joules per gram degree Celsius, and this is just joules per degree Celsius. Because bomb calorimeters are so carefully set up that way, they always know how much water is going to be in there. They're very well constructed. They're much, they're not incredibly expensive pieces of equipment. They're only a few $1,000s, as opposed to tens of thousands of dollars or hundreds of thousands of dollars. But still, they are well constructed, very sturdy, very well maintained and calibrated pieces of equipment. So instead of MC delta T for a bomb calorimeter, it's C delta T. So otherwise it's very similar. The heat change of the reaction is negative heat change of the water, so it's negative C delta T. So for example, if you have sugar, okay, calorimeters, this is actually how they measure calories in food, is with a bomb calorimeter. They just take a piece of the food and they burn it inside of a bomb calorimeter. So what is the enthalpy change for sugar? If you burn 10 grams of sugar in a bomb calorimeter with a heat capacity of 30.046 kilojoules per degree Celsius, it raises the temperature from 20 to 25.182 degrees Celsius. What is the enthalpy of reaction for sugar? So let's go ahead. Jason asked his question. Is there a reason why the exam is moved to Thursday? I don't know. I don't know why they moved it to Thursday. And yes, you are seriously expected to take 3 exams in the space of a week. It's just the thing that happens. It's painful. I know it's difficult, but it's how things happen. I'm sorry. As for why they moved it to Thursday, I don't know. There's, I haven't checked my email yet today. There might be something in there. But it's just the way things are. Sorry. All right, so let's look at calories in sugar. There we go. All right. So delta H is still going to be Q of the reaction over number of moles. So that's negative C delta T over N. So C is 30.046 kilojoules per degree Celsius. Delta T is 5.182 degrees Celsius. And the number of moles, we had 10 grams of sugar. And sugar is 180.0 180.15 grams per mole. So now we can plug all of those numbers into our calculator. So 30.046, oops, you might help to show the calculator to you while I'm doing this. 30.046 times 5.182 degrees Celsius divided by 10 grams divided by 180.15 grams per mole gives us 2,805 kilojoules per mole. So that is a much bigger number than the neutralization of the acid and base we looked at before. The acid and base we looked at before was about 57 kilojoules per mole. This is 2,800 kilojoules per mole. And yes, that is appropriate. That's what you expect. Neutralization reactions don't generate nearly as much energy as a combustion reaction. That's what this is a combustion reaction. It's going to generate a lot more heat. So that is how we do calorimetry problems. Just depending on what kind of calorimeter, it's going to change the formula that we're looking at. For a constant pressure calorimeter, it's MC delta T. For a constant volume calorimeter, it's just going to be C delta T. Either way, be careful about the sign. Remember that the temperature we're measuring is the temperature of the solution, which is going to have an equal and opposite thing for the reaction contained in the solution. Remember, we care about the reaction, but the reaction is dissolved in the water. The water is the surroundings. We're measuring the surroundings, And remember, thanks to the first law, energy change of the system is equal and opposite the energy change of the surroundings. And that is it for today. We'll cover another set of lectures tomorrow. See you around. I will hang on for another 30 seconds in case anybody has more questions.